of the expectation of u given big X equals 0. The expectation of u given big X equals 0 yields the covariance of X and u equals 0. And faux, I think that is faux sub big X sub u equals 0 proof. The covariance of big X and u equals the expectation of big X and u minus the expectation of X times the expectation of u. The expectation of X and u equals the law of iterated expectations, which is the expectation of the expectation of X and u given X equals the expectation of X times the expectation of u given big X equals E of big X times 0 equals 0, because the expectation of u given big X is equal to 0. The expectation of u equals the expectation of u given big X equals the expectation of 0, which is 0. Covariance of big X and u equals equals the expectation of big X and u, which we know equals to 0, minus the expectation of X times the expectation of u, which you also know equals to 0, equals 0. Information on big X is used up. The unobservable u is unrelated to big X. Open bracket, big X sub I and big Y sub I, close bracket, from I equals 1 to n is a random sample, and hence independently and identically distributed. Random sampling is a key assumption for the LLN and the central limit theorem. Reasonable in many settings, but not always. Data recorded over time, for example, GDP, data from networks, for example, Facebook friends, and non-randomized experimental data. Large outliers are ruled out. Technically, the expectation of big X to the fourth power is less than infinity, and the expectation of big Y to the fourth power is less than infinity. See stated do file figure underscore outlier dot to do to replicate this figure. Linear regression when there are outliers. Original data and data modified with one outlier. Fitted values. Interesting. Beta sub 1 equals 2.2 and beta sub 1 equals 5.1. The sampling distribution of ordinary least squares estimators, 1 of 4. If the ordinary least squares assumptions 1 through 3 hold, recall that big Y sub I equals beta sub naught plus beta sub 1 big X sub I plus u sub I. Beta hat sub naught equals a big Y bar minus beta hat sub 1 big X bar semicolon beta hat sub 1 equals S sub big X. I don't know if that's big X. Restarting that. Beta hat sub 1 equals S sub XY and over S squared sub X. And that equals a term over another term. The first term, the numerator is 1 over n minus 1 times the sum from I equals 1 to n of open parentheses big Y sub I minus big Y bar close parentheses open big X sub I minus big X bar close. That's the numerator. The denominator is 1 over n minus 1 times the sum from I equals 1 to n of open big X sub I minus big X bar close squared. Let's focus on calculating the expectation of beta hat sub 1 and variance of beta hat sub 1 first. Then we can appeal to the central limit theorem. Note, open big Y sub I minus big Y bar close equals beta sub 1 open big X sub I minus big X bar close plus U sub I, since U bar equals 0. The sampling distribution of ordinary least squares estimators 204. If ordinary least squares assumptions 1 through 3 hold, beta hat sub 1 equals the sum from I equals 1 to n of open big Y sub I minus big Y bar close open big X sub I minus big X bar close over the sum from I equals 1 to n of open big X sub I minus big X bar close squared equals beta sub 1 plus a term with the numerator and the denominator, and the numerator is the sum from I equals 1 to n of open big X sub I minus big X bar close U sub I. That's the numerator. The denominator is the sum from I equals 1 to n of open big X sub I minus big X bar close squared. Using the expectation of U given big X equals 0 and law of iterated expectations, the expectation of beta hat sub 1 equals beta 1 plus the expectation of open bracket, the expectation of open, there's a term with the numerator and it is the sum from I equals 1 to n of big X sub I minus big X bar times U over the sum from I equals 1 to n of open big X sub I minus big X bar close squared given big X. And we know this equals 0 because the expectation of U given big X equals 0. And we close the bracket equals beta sub 1 unbiased. The sampling distribution of ordinary least squares estimators 3 of 4. If ordinary least squares assumptions 1 through 3 hold, now calculate the variance of beta hat sub 1 equals the expectation of beta hat sub 1 minus beta 1 close squared. The expectation of beta hat sub 1 minus beta 1 close squared equals the expectation of open bracket with a numerator and the denominator, the numerator is open 1 over n minus 2 times the sum from I equals 1 to n of open big X sub I minus big X bar close U sub I close squared. The denominator is open 1 over n minus 1 times the sum from I equals 1 to n of open big X sub I minus big X bar close squared close squared close bracket equals epsilon equals the expectation of s squared sub ux over s squared sub x, and then that term is squared. Or denominator more clearly reads open s squared sub x close squared, and that equals the standard deviation of beta hat sub 1, or sigma squared sub beta hat sub 1. Hence, using the central limit theorem, the square root of open beta hat sub 1 minus beta 1 close approaches d distribution, I believe, normally distributed with mean 0 and variance sigma squared sub beta hat 1 sub 1. The sampling distribution of ordinary least squares estimators, 4 of 4, remarks similar approach to calculate the square root of n of beta hat sub naught minus beta hat, restarting that line, similar approach to calculate the square root of n times open beta hat sub naught minus beta sub naught close approaches the distribution of big N of mean 0 and variance sigma squared sub beta hat sub naught. See book. Note sigma squared sub beta hat sub naught, comma sigma squared beta hat sub 1 are population moments. We can use sample estimators to get sigma hat squared sub beta hat sub naught and sigma hat squared sub beta hat sub naught. In the special case, the variance of u given big X equals the variance of u equals sigma squared sub u, and there's the upside down a and an I, homoscedasticity. Then the expectation of open bracket open 1 minus n minus 2 times the sum from I equals 1 to n of open big X sub I minus big X bar close u sub I close squared. That was the numerator. The denominator is open 1 over n minus 1 times the sum from I equals 1 to n of open big X sub I minus big X bar close squared close squared. Close bracket is approximately the expectation of open bracket with the numerator and denominator. The numerator is 1 over n minus 2 times the sum from I equals 1 to n of u sub I of u squared sub I. The denominator is 1 over n sub 1 times the sum from I equals 1 to n of open big X sub I minus big X bar close squared close bracket, equals the expectation of open bracket S sub, open bracket S squared sub U over S squared sub X. And that's close bracket, open close bracket around that. By default, statistical software usually relies on this simpler formula. Best not to. In Stata, we use option VCE robust. Final observations. The higher V of X, the more accurately the slope estimated, and the higher the big R squared. To see this, note that the variance of big X appears in the denominator of sigma squared sub beta hat sub 1. Linear regression as a function of the variance of big X. Variance of big X set to 1, variance of big X set to 0.25. On the left, estimate of beta hat equals, estimate of beta 1 equals 2.0. Standard error of beta 1 equals 0.1. And where the variance of X is set to 0.25, the estimate of beta sub 1 equals 1.8. The standard error of beta sub 1 equals 0.4. True value used in the simulation is beta sub 1 equals 2. Sample size set to 0. See Stata file figure _ VX.do.